Hello, good day. On behalf of the Institute of Civil Engineers of Costa Rica, we would like to welcome you. So for today, we are gonna have a webinar that it's a contribution of the UK group of IAPSE, and we are gonna have first a words of Matias Valenzuela on behalf of the IAPSE.
Thank you, Daniel, and welcome to this webinar. So it's on behalf of the IAPSE Association. Let me give you some words to start pre-Congress webinar, because this year we will have organization.
I think that we are having some problems with Matias' connection. But so we are gonna have the Congress in Costa Rica on September
of this year, San Jose.
Okay.
I'm sorry.
Go ahead. We lose your connection.
Oh, maybe we have. Yeah, sorry. So IAPSE is an association with over 90 years that have many importance in the field of the structural engineering and also bridge engineering. And we are looking for always to make a very good networking with all the important and structural engineers all around the world, and of course also provide some kind of support and guidelines for improve the civil engineer in the different countries. So that is really important to know how is the contribution of our association to the engineering in general. No, so as I mentioned, we have this nice opportunity to have a webinar coming from this kind of link between different countries. In this case, UK, with the engineer Knight, that could provide some words about of the, or at least some kind of thinkings about of spanning, craft, and collaboration for the design future. So that is really important, and it's part of our scope to link and, of course, think about of what will happen in the future and the design. So again, thank you for the interest to be part of this webinar, and of course to also have the chance to be part in our next Congress in San Jose, Costa Rica. We really waiting for you, and of course I hope that you enjoy this excellent lecture in this webinar. So thank you, Daniel, for this chance to talk about that.
Thank you. So for today's webinar, the title is Future Spanning, Craft, Collaboration, and a Future of Design. The speaker is going to be Engineer David Knight. David is Director of Design at Cake Industries, a chartered structural engineer and principal of Cake Engineering. His specialism is in engineering design for fabrication in the field of complex sculptures and bridges, with a particular focus on movement structures. So David, thank you very much, and we will enjoy your webinar.
Thank you very much. And it's really a delight to be here to talk to you all, and hopefully I'm coming across loud and clear, and you can see my slides, and everything is working well. As Danielle said, I'm David Knight. I'm the Director of Design and Engineering at Cake, and I wanted today to come and talk about the future. It's easy to feel that the future is dystopian. Climate change, AI, politics, social cohesion, pandemics, there's much to worry about. A global survey from 10,000 young people in 2021 said that 60% are suffering from a form of eco-anxiety, the chronic fear of environmental doom. In engineering, we oscillate between head in the sand, business as usual, and believing that we can be the ones to drive change in a better world. However, construction's changing, and construction's changing rapidly. In bridge engineering, we're perhaps a little bit behind the wider industry, but those same winds of change are still likely to affect the way that we operate over the next 10 years. In this talk, I'm going to try to outline one possible future of what design, a utopian vision, perhaps, but one that relies on what humans do best. The public advent of generative AI, artificial intelligence, has taken a lot of people by surprise, and there's been a lot of media attention and quite ill-informed journalism and writing about how it will take our jobs. AI is a very coarse tool. These are images from DALL-E, a ChatGPT version for photos, and it shows that it's not immediately going to replace designers. In fact, it's probably almost as bad as the renders that Google shows up, but it's perhaps a realistic view of how we maintain our structures. The initial uses of generative AI are somewhat mundane. They're probabilistic, i.e. they're based on what the most likely thing to have happened previously in its data set, rather than deterministic. It's not particularly innovative. It can only respond to the unexpected by referring back to how that might have been approached before. However, you can start to glimpse the power of it as a tool. And tool is the right word. Generative AI is currently a tool that assists in the boring work that we do and augments and smooths the interfaces that we have with technology. It's educative, and it bypasses traditional gatekeepers of knowledge, i.e. jargon, paywall, even engineering institutions. It allows that to be free access to the rest of the world. As a tool, it's already having a revolutionary effect. This tool is on the market in the UK. It's an automated timber floor designer. It automatically locates beams, panels, and other structural elements. In this particular industry, so timber flooring, projects in the UK are won or lost on a less than £100 price difference. And so these very small advantages are really beneficial to that industry. It feels like a revolution, but engineers are good at revolutions. The last revolution in the UK, the advent of building information modelling, 3D modelling, in the UK, that was government required 8 years ago, which seems such a long time ago now, shows that the industry can change and adapt. We all work in object-orientated information models, and it's now commonplace and expected in the way that we work. And engineering assimilates these tools into its workflow. If we go further back, the advent of the pocket calculator and the personal computer, widespread use of FE, finite element, and more recently carbon calculations, data monitoring, have all been viewed in revolutionary terms. But each of these are tools that we now have on our desk or on our desktop. Tools and the way that we use them, and actually the way that we get better at using them, are what defines craft. At Cake Industries, we work right at the intersection between craft and design. We're a combined engineering and fabrication business, and we generally make what we design. We treat tools with reverence and take time to learn how to use them. This might be a hand chisel, or it might be a new piece of software. Tools open up opportunities. By understanding what it can do, our designs get better. However, our designs are only as good as the human operators, and the best projects only come about when all of those are singing together. I'm going to take you through two particular projects that we are really excited by. They are Bracklin Falls Footbridge, which we worked on with Beam Architects. Cake Engineering were the engineering lead, but we were also, as Cake Industries, principal contractor, fabricator, and installer. And then I'm going to talk about Cody Dock a bit later. Bracklin Falls is a small footbridge in a beautiful part of Scotland. It's a stunning sight, a waterfall that flows through an ancient woodland. And as you can see from this image, it's fairly remote. And after a site visit, we became very aware that the only construction access to site was around this very tight hairpin bend, a very steep hairpin bend as well. And we had to get all of our equipment and the bridge itself onto site around this corner. That's a LiDAR scan taken with an iPad. We're able to use that to plot plant movements, work out what is feasible to get around this corner, and work out that this is the key constraint for the entire project. This led to a kit of parts, a sort of IKEA-like flat pack bridge that was made up of small 3-meter long segments that could be bolted together once they were on site, rather than bringing long 20 meters pieces around this corner. But that kit of parts, or that flat pack idea, went further. We decided that to really utilize our skills of fabricators, we would think about how the beam was made. A typical plate steel sheet in the UK is about 3 meters by 1.5. There are other sizes, but this is a good, very familiar and very cost-effective plate size. So we decided to get our main structural beam out of this one plate and trimming it down, and then folding the top edge and folding the bottom edge gives us a Z shape, and that Z shape approximates to a beam. The web is obviously the same thickness as the flanges, and that gives us the opportunity to take out material there, perforate it. The web is obviously not working as hard as the main flanges, and those perforations will become visible later on in the rest of the structure. Folding steel is something that we do quite a lot as Cake Industries, but it's not common practice, I know, in large scale bridge engineering. But the machinery is there. These are a variety of different machines. You can see the scale of some of these operations. And the machine at the top, the Gemini machine, is a plasma cutter and a milling combined with a milling machine. So we were able to use one machine to provide a computer-controlled pattern to that machine, to a steel plate, cut out our panels, and then put them through a press brake to fold them into shape. These panels had welded end plates attached, which were then attached to cross beams, and the cross beams and U-frames stabilized that system, making a very traditional through girder bridge, a U-frame through girder bridge, with a lightweight glass fiber reinforced polymer deck that went on top of that structure. Construction took place in the dead of winter. It's -5 degrees centigrade in January in Scotland. So icy weather and very hardy construction workers working here. But with the access issues came temporary works issues. How are we going to get this bridge across? And you can see here we had some rocky outcrops, and were able to install a temporary set of rails before building our modular system and slowly push launching that piece by piece over the gorge. And this goes back to that thing of the corner driving the design. We couldn't get a crane down to site. All we had was this small excavator. And so the design is driven by what the site requires, but is also reflective of the architecture and the beauty of the location. We were using Corten, or weathering steel, which is as I'm sure you know, a material that weathers and creates a stable rusty patina. It stays rusted, colored orange, but that doesn't flake off, and therefore is a long-term durable solution, meaning that we don't have to repaint this structure over the waterway. and it fits in well with the tree-lined environment that you can see, the ancient woodland, which was a beautiful part of the site. But that architecture piece is as important as the construction piece. While we may have designed this for being easy to construct and easy to fabricate and cost effective, we were really conscious that we're putting in place something that is there to last for 120 years. And the bridge itself, while simple in form, has lots of touches that, working with Beam Architects, we were able to introduce. These include the perforations, which you've seen, and the handrail and the way the beams themselves lean out. These end pieces you can see on at the front of this image that smooth what might be quite an abrupt entry, but also that we were able to fabricate, but because the bespoke panels and the perforations in them are all individually cut out, we were able to vary the perforations across the beam. So in some places they were denser than others, and in some places the perforations made a window. And here we were really conscious that people hadn't come to this site to see the bridge; they'd come to see the waterfall. And you can just about see in this image that this triangle in the middle has larger holes, and therefore gives a better view through that transparent panel down to the water below. The modular system we designed here then has moved on to become a product. It's something that we can reuse again and again. It was such a successful construction process that it's something that we're imagining and encouraging can be used elsewhere. So we have these are renderings of possible sites, and we're currently in talks with a few different locations as to where this might go. The human skills that I'm talking about, that are really what I view as the core of engineering design and the future of engineering, include things like empathy and collaboration and excitement. And this next project, Cody Dock Rolling Bridge, really exemplifies those human skills. It's a project we carried out with Thomas Randall Page, who's the architectural designer, and Price and Myers as the main concept structural engineer. Cake Engineering did the detailed connection design, and then Cake Industries fabricated and installed and acted as main contractor for this structure as well. And I don't know whether you know of this bridge, but it's a bridge that started as an internet meme. It's a bridge that many of us looked at and thought, that's a lovely idea. I wonder how that works, but I really can't believe that we will ever see this bridge in reality. This was about 7 or 8 years before construction started, and Tom, the architectural designer, took a long time to encourage the client and generate enough funding for this bridge to come to fruition. But ultimately he did, and we got charitable and government funding to create this structure. Unfortunately, that came with a time limit, and so we only had 7 months to complete the detailed design, fabricate and install the structure. So it was a very intense period, but ultimately quite a successful outcome. And it relies on the concept of a square wheel rolling along a track. This is a mathematician, an American mathematician called Stan Wagon, who proved after Maxwell that a square wheel can roll as long as it has a perfectly shaped road. And if you have a perfect square, the road is a set of upside down catenaries, and then the square will roll along it. As you saw from the render, there were squares at either end of the bridge, the hoops. But why is that useful for a bridge? Well, if you exactly balance that square, so you have the same weight at the top of it as the bottom, the center of mass is in the middle, and the center of mass does not go up or go down. And therefore, for a moving bridge, you're not putting energy into this system to lift mass. You're only putting energy in to start or slow down motion, i.e. inertia, and to overcome friction. And that means that this leaves the structure within the moving parts of the structure within the realms of what can be done by humans. You can wind this bridge individually by yourself by winding a winch and pulling it upside down. Now, the maths of the square-wheeled bicycle may be quite simple as catenaries, but as soon as you put a radius on the corner, everything becomes much more complicated, and you get to elliptical integrals and things that need to be solved in a very complex, iterative way. I am no expert on this, but it does lead to some quite beautiful maths. As always with these structures these days, it really ended up as a mess of grasshopper scripts and geometry definition in Rhino. But the output is stunning. This is a diagram which shows the path of the teeth as they interact with that toothed wheel. And we use this path to generate the tooth profile for each of the teeth around that hoop, and carved out the direction of travel of those teeth. Talked about the pins. The pins sit along the abutment. They stop the bridge sliding along the interface. The bearing interface, i.e. where the bridge rests, is separate and sits inboard of that on the concrete abutment, but there is a steel template that defines the geometry there. Most of this structure is very lightweight, but we're talking 4 or 5 millimeter thick steel, and we've cut out as much material as we can out of the deck just to reduce that weight. Again, made out of weathering steel and quite a slender steel box with teeth attached and the hoops on either end. This was all modeled in 3D. This is a fairly normal process nowadays for us and for lots of fabricators. This was done in SolidWorks, which is often used for mechanical engineering, but it allows us to be incredibly accurate with our 3D modeling, especially for plated structures. And in this image, you can start to see some of the measures that you put in place to control the fabrication tolerances. So all of these dots on the bridge deck you can see here are tab and slot holes in the plate of the bridge deck that perfectly align the stiffener underneath with the plate on top and allow a very tight control of tolerance, because this project was really all about tolerance. Moving a structure of this scale and rotating it upside down relied on lots of things being right, and one of those was that everything was accurate to what we expected. If the two abutments were towed in or twisted or moved up and down relative to each other, it just wouldn't roll. And so control of tolerance was vital. We split it into 4 parts for fabrication, 2 hoop tops and then 2 deck pieces. And those were fabricated in our works in South London, welded together and piece by piece. Things were test fitted, fits and checked. Things were turned up and upside down, welded, ground flush. Pieces were added. The tracks were welded very accurately in the same location, and it was very carefully pushed out of the door. It just fits out of the door in our works. Taken by road to site and then assembled on location. But going back to tolerance, we were main contractor. We were also civils contractor, and what this video doesn't show is the abutments, which were made using traditional formwork and concrete, but it was formwork made by furniture makers. And going back to this idea of craft and using the right tools, this enabled us to use people and tools that, yes, aren't normally used for formwork, but can create incredibly accurate forms that are accurate to plus or minus 2 or 3 millimeters rather than plus or minus 25 millimeters, which is what civil works normally are. This was one of the most nerve-wracking days of my career, watching this bridge roll for the first time on the tracks. My colleague there is checking every single pin as we roll it over, looking at the interactions between the pins and the teeth, and it does actually roll quite nicely in the end. You can see the scaffolding deck there. That was a temporary piece to allow us to install it, and that was removed afterwards. And the bridge is a key part of this environment. This is a site in East London where an artist's community is being set up, and this was a way of generating interest and attracting people to that site to create a community. And it has been very successful. And it is manually wound. And you can see here the hand wound winch at one end. The other end you can see is another winch where you pay out a cable just to loosen it off. And then to reverse that, you obviously wind in the other direction. A tool is but the extension of a man's hand, and a machine is but a complex tool. And he that invents a machine augments the power of a man and the well-being of mankind. If you forgive the gendered language, this quote from 1887, I feel really reflects how tool use particularly is changing the world in which we live. The changes that are happening are opportunities as well as threats. Tools are becoming more human, but they're still tools. Tools also change the way our brain works, but we have to be really wary of what is best for the machine and make sure we're designing what is best for humans rather than just believing what is best for the machine. The worst excesses, I believe, of parametric design stand as a warning about what happens when we let the machine drive the design without taking humans into account. Alan Turing said, "The human mind is special, not particularly because of its computing power, but because the body provides it with an interface to the world." As Turing says, computing power is not everything. What is special is the way that we relate to the world. Human-led and human-centered design has to properly consider the greatest threat to our society, the climate emergency, of course, and the biodiversity breakdown. Traditionally, the Institute of Civil Engineers, which is the institution in the UK and worldwide that deals with civil engineering, had as its guiding principle that civil engineering was the art of directing the great sources of power in nature for the use and convenience of man, which is a fantastic, evocative way of talking about engineering. However, we should really ask what design should be in the future and what our ethical responsibilities are. We have moved beyond working out what our tools can do, because our tools can do almost anything. We need to be deciding what they should do. In 2018, it was proposed that we updated that guiding document for the Institution of Civil Engineers to the art of working with great sources of power in nature for the use and benefit of society. And it's important to think about this. What is good for society? What is good for us engineers? But what is good for the planet? How do we as engineers mediate between the desire to do exciting things with the climate responsibility to do as little harm as possible, and hopefully the climate responsibility to do good and regenerate the world around us? Do we think about taking on things like jobs designing a new airport, or do we limit ourselves to jobs and work that really does reward and improve the wider human race? 7 years ago, I wrote an article that appeared in the Structural Engineer, a magazine in the UK, about what a structural engineer would be in 2050. I was younger then. It was still interesting to reread it. It severely underestimates the progress that we have made in the time since. It is only 7 years, but it mentions virtual meetings, only occasionally coming into the office, queued analysis models on the cloud. It talks about resource scarcity and water scarcity and tall timber buildings. I take from this that the world can change dramatically in 10 years. And actually, I see that as a positive. We can make the changes that we need to make in the next 10 years to address the climate emergency. To me, that means focusing on craft. Yes, the use of tools and revolutionary approaches, but also about getting better in the service of what humans are good at, and which is making human-centered and not machine-centered decisions about the world around us. What should engineering become? And what are our ethical responsibilities to those that follow us? The utopia we're heading towards is not defined, it's not visualized yet, but we do need to give it some serious thought. It's within our power to achieve remarkable things, but we need to collectively buy into answering these really big questions. Thank you very much.
David, thank you very much for your webinar. Everything was very, very clear. Here in my WhatsApp, I have two questions. I will go with the first one, and it's related with the square wheel. So how did you end up with the square wheel? With the square wheel, it was like a brainstorming at the beginning. It was like a kickoff that you were dealing about this, and if you have like another possibilities that were taken into account before this.
Yes, there was a big conceptual design process. We weren't actually appointed at that stage. The architect was did a lot of that work. The original plan from the client was to install a very traditional Dutch bascule bridge, a lifting span. But Tom really wanted, as the architect, really wanted to try something quite innovative and quite new. Now, rolling bridges in this way, where you roll along a track, have been done before in Belgium. Everything's been done before in Belgium, but they are with round hoops at the end rather than square hoops at the end. The thing about a round hoop is that if you have a set deck width, that the circumference of the circle is a certain distance. What a square does is shrink wrap that. So actually, the circumference of the square was the circumference, the length of the square, i.e. the length of the track, is shorter than it would be with a round circle. And that length meant that we could fit it in the dock length that we had. So there was a rational reason to go from a round circle to a square. That square, of course, gave us lots of engineering challenges, which was part of the fun. And when we were appointed, and when Price and Myers were appointed, it was an incredibly collaborative process to solve the problem that we had been asked to solve. And it was one of those wonderful projects where you go into meetings and you leave the badge at the door. You leave, whether you're a structural engineer, whether you're a fabricator, whether you're a contractor or an architect, and you go in and you solve the problems that the project needed to solve. And the square was what it was, but it makes a beautiful object.
Excellent. The second one is related with ethical responsibilities, and sometimes the problem that we have is that sometimes we call it like the chromatic engineer, and sometimes when you run the software, and there are some engineers that they just look at the colors, and if the color is red, immediately the engineer changed the steel section.
Yeah.
But sometimes our concerns are about that. We feel that sometimes engineers are using software as a black box. And the problem is that when you are using software as a black box, is that garbage in, garbage out. So I think that regarding ethical responsibilities, we would like to know what's your opinion about that?
I think it's hugely important. I think all engineers have to have an ethical responsibility and an ethical understanding of what their role is. They are not just people who run computer programs. An engineer should be a professional. We are a respected voice in construction, and we have to take that responsibility really, really seriously and really personally. I don't think we should be building things unless we fully understand the physics, not just the maths behind what we do. And by physics, I mean, where does the load go? Why is it going there? how does this building respond as we prod and pull and push it? And one of my mentors said to me that the physics is actually more important than the maths. The maths is just how we show that we know what we're doing. But if you get the physics right, that's much better. And I think we get seduced by computational programs that give us pretty colored plots. But yeah, you're completely right. Garbage in, garbage out. We have to be better than that.
Exactly.
Otherwise, there is no point for us as engineers. That's the only value. And you know, in some ways, I see that the engineers that think that way, that put more steel in because the computer says so, are the ones that are the first ones that are going to be made extinct by AI and computational advances. I think to be valuable in a world that's changing, you have to be both ethical and advanced and thinking about our impact. And that I think is really important. You need to be a valuable member of the wider society.
Excellent. And the last one is a comment and a question of engineer Arce. So first of all, deep appreciation for such an illuminating set of concepts, empathy, collaboration, and excitement. I completely agree on the dramatic importance of those attributes. The question is, how are companies and universities in the UK dealing with the challenge of embedding those attributes in engineering education? Wow, that's
it's a really big question. And
yeah.
I have to say, I'm not an educator. I hope that these concepts are being embedded. I think the passion for engineering is really important. I think you have to want to love what you do. And I think that is embedded in some engineers. And you see that as they graduate and they grow up and they become part of the profession. There are a few universities in the UK that are exemplars, I think, of making those connections and making collaboration part of how they work and how they teach. And I would pick out both Bath University, Imperial College, and the University of Sheffield in that regard. There are also moves afoot at the University of Cambridge to integrate architecture and engineering and material science as a single design degree. So education in the UK is changing, and I think we are all appreciating that you can't just teach the maths side anymore. It's not enough to know WL squared on 8, although that's a very good start, because that doesn't get you very far if a computer can do that. You have to teach people firstly how to learn, because they will be continually learning, as I've been continually learning throughout my career. But you also have to teach them how to be curious and how to be passionate, and how to work with other people. And if they sort of master those skills and have a good appreciation of physics, I'd much rather that than they come out with in-depth knowledge of the latest computer programming, because that can all be learned. I'd much rather they were passionate and engaged members of our profession.
Excellent. Well, so Engineer David, thank you very much for your presentation. Muchas gracias. And well, for all the audience, hope to see you on next weeks, because we're gonna have more pre-Congress webinars. So thank you very much again, and we'll have a good day.
Thank you. Really good to talk to you all.
Bye-bye.